forget about the dielectric for the first part. Okay, what about in just in terms of maybe things on this side? I'm going to ask you to think about the charge on the this.
What is the second or Q over
Okay, Q over E naught A. Q over epsilon A. Yep. Okay. What do I know about the, related to that, what do I know about the electric field in the dielectric? There's a number of ways I can express this, but there's one in particular that's kind of useful. Yeah.
Can you manipulate the whole sigma over E0 minus sigma induced over E0? Or is that where you're pointing towards?
What do you mean? I'm not pointing to anything. Yeah, okay, so I know that the electric field in the dielectric is modified by this, okay? So this is E naught over kappa, and E naught I know is already this, so it's Q over, this is kappa A. So if I knew the area and I knew the charge, this would be a fairly fast way of getting to the answer, right? So I need to know both of these things. Well, what do I know? I sure don't, I don't yet know the charge, but I do know the area, and I realized I was not very crisp about defining what the area was. But the plates are rectangular in this case, and apparently they have size 20 by 28 centimeters, so it looks like these two guys against each other. All right, so I do know the area. But I don't yet know the charge, so I know this, I know kappa, obviously I know epsilon, but I don't yet know the charge. So how could I find the charge based on what we've kind of talked about before? Yeah?
We can use Q is equal to CV, and we know the equations for the capacitance in the gap and the capacitance in the
All
diode.
right. So again, this was intended to directly follow on from the first example. This would be a nice way of doing it, because I'm given a potential difference, of course. I don't yet know this, but this is the same geometry as we had in this problem. And a reminder, we treated this as like two separate capacitors in series. We know that these are the parameters, and the end result that I got here is all of that. So I could make this now Q equals all of that. Times V. So am I good? Presumably yes. I know this. I know the relative spacings. I know the areas. I know kappa. It's a little bit of a tedious calculation. So in principle, I know all of this stuff, so I can figure out the charge. So then I can go back and plug all of this in, and just again, because it's kind of maybe nice to have some numerical answers at the end. It turns out if you do this, and this would be a fairly typical calculation for a capacitor with a dielectric. It turns out the field in the gap is about 5 times 10 to the 4 volts per meter, and the field in the dielectric is simply this reduced, and it's about 2.5 times 10 to the 4 volts per meter, because it's reduced by a factor of kappa, which is 1.8. Okay? So, again, it's not the only way, but it might be one of the easy ways of figuring out solid parameters to make two-ingredient capacitor. Right. Ariel.
Does the E naught equal the E gap? Like, wouldn't the E naught be the, not this gap, would be the whole distance of the air?
It's the same.
It's the same.
Yep. Yep.
Is charge with every single part like the same magnitude? This is what we're saying.
It's not, but we kind of embedded it in going through all of this, right? So we found out eventually that we can put this in, and we need the kappa factor that will take account of it. So it's a good question, but it's not the easiest thing to answer unless you just work your way through this. So we do expect that the induced charge on the surfaces of the dielectric is not equal in magnitude to the intrinsic charge that's on the capacitor plates. But that's embedded in this derivation. Okay, so that's all we're going to talk about for capacitors for a while. We've explored their energy storage usage primarily. You've heard me say more than once that they also have a secondary storage use, which is when we combine them in electrical circuits with other components, they introduce some time-dependent behaviors. We're going to come back and talk about that after spring break. So in the remaining 10 minutes, I want to turn our attention now to a new topic, which is really the starting point of the entire remainder of the semester, which is what happens when charges are actually in motion. Okay? So we've really not had cases where, other than for instantaneous effects, charges are in motion. They've been static. And the instantaneous effects I mean is those cases where we dump a bunch of charge on some object and the charge instantaneously, for all intents, distributes itself to wherever it wants to go based on Coulomb repulsion and Gauss's law. But other than that, we don't have ongoing motion of charges. So now we're going to turn our attention to cases where we do. And of course, this is what's known as a current motion of charges. So there's a fair amount of introductory stuff to talk about. So let me get started on that. And of course, it'll occupy us as soon as we're back after the break. So first off, I'm going to be talking about a net flow of electrical charge. So the charge is in motion. Okay, so this has to be a net flow of charge. I've been kind of a little lazy, maybe lazy not the right word, remiss in talking about the realities of conductors. We need a conductor if charges to be in motion. So we've allowed conductors to have positive charges move arbitrarily, negative charges to move arbitrarily. In fact, it comes back a little bit to the comment I made about, or the question I asked about what do you expect the dielectric constant to behave like in the function of temperature. If you think of a conductor in terms of metals, a couple of things to introduce a bit more realism into our understanding. First off, it turns out for almost any material, it's not true that the negative and positive constituents have equal mobility, equal ability to move under the influence of an electric field. And as I think all of you know, for typical metals, what's actually happening is that what's really moving are only the negative charge carriers, electrons, and the positive charge carriers, so the atomic nuclei, are pretty much stuck in place. So that's one very important distinction we can talk a little bit more about before we wrap up, and certainly after the break. The other thing to keep in mind is that these are fundamental constituents in our metal, and as such, they are at some ambient temperature, whatever that happens to be. So even without an electric field being applied to maybe preferentially drift one type of charge carrier, you should expect that the constituents are in thermal motion always. And of course they are. So the constituents in a chunk of metal are without an external electric field. They're in motion, the electrons are in motion, but they're in what I would describe as random motion. In arbitrary directions, they'll move, they'll crash into a positive ion in the metal, they'll bounce off. So there's this kind of random, almost Brownian type motion going on. So when I talk about a net flow, it doesn't mean that type of random thermal motion, it means there's an overall migration of one charge carrier. So that's what we mean when we talk about current. So it's very easy to imagine how I might do this sort of conceptually, but also in reality. We still haven't quite yet defined what one of these batteries is. That's coming soon. But we do know that it's something that provides a potential difference between the two terminals. And so if I took a battery and simply hooked up a conducting connection between these two poles, we're going to expect charges to move. Now, we're going to go back and forth between conceptual and reality. I will try, hopefully not to make that too confusing. But if you think about this, this is going to tend to, let me say, attract negative charges, and this is going to tend to attract positive charges, at least conceptually, if our conductor, this loop here, is made up of something where both the positives and negatives can move. That's what we expect to happen. So we expect to set up these currents. Again, in practice, it may be just one actual charge carrier. And I want you to get into the habit of not being scared by the fact that whether or not both signs of charge carrier are actually moving or not, the end result is kind of the same. So whether they're both moving or whether just, let's say, the negatives are moving, the movement of the negatives sort of leaves behind a, let me say, a surplus of positives. So it's can be treated in exactly the same way. And that sort of conceptual idea of recognizing the motion of just one charge carrier as effectively being the same as the motion of both signs of charge carriers in opposite directions, we're very much going to kind of pass through the remaining minutes of today and into next time. So, let's say we've got net flow of charge. We're going to define this right off the bat as the current. And let me put it already in differential form. It's the rate at which charge moves past some reference point. So maybe I kind of just flag some random point here, and I've got a little microscopic beam counter who's counting charges as they move by. And that person simply counts how many charges pass by that point in a given time interval. That's what we're going to define as the current. Okay? So that's our definition of electric current, rate of passage of charge. And it's not a bad time for me to remind you of something I said 3 weeks ago, probably. This is actually the practical basis of the definition of electrical charge. So let's say this is constant. It's just amount of charge per time. If I flip this around, of course, I get that charge is just I times t. This turns out to be the actual definition in the standards world of charge. It's a little weird. It comes backwards. It actually is defined by current. The reasons for that are really practical. Just an aside, it doesn't matter. Okay, so SI units. We've got coulombs over seconds. So coulombs over seconds. That's our unit. And as always, we're introducing something that's very common. We're going to define this with a new name, and it's the amp, and abbreviated just as capital A. Okay, so amperes is our SI unit of current flow. 1 ampere is a large amount of current. 1 coulomb of charge passing a point in a second is a very large, pretty much large amount of current. So amperes is a hefty amount of current. Okay, so it's a scalar quantity, and this is going to introduce a little bit of confusion, I predict. It is obviously just a number, a magnitude, coulombs per second, amperes. There's not intrinsically any directional information in this, but in practice, we're always worried about what direction current is flowing. So keep that in mind. It's intrinsically a scalar, but direction is definitely important. Okay, so remaining minutes before the break. Let's see, what do I want to say about this? There's a convention. This goes back to the time of Franklin and all the people who were really starting to make electrical phenomena applicable to the wider world. There's a convention that's adopted since that time. The current is drawn in the direction of positive, or defined in the direction of positive charge carrier motion. Okay. So, I'm going to stop. I do not want to run over on your last day before the break. So I want you guys to read ahead as always. The reading ahead is posted so that next time after the break, it's about current stuff, and we'll obviously pursue that in the week after the break. Okay, that's it. If somebody could turn off the video camera. No, thank you. Not much to say, other than have a fun break, and we'll see you in